But the idea now is that we want to kind of take this and look at a couple different examples. We'll consider the damp nonlinear pendulum from the previous class, because this is a physical example that is very important to understand, and also it gives us an idea of what's often a very convenient Liapunov function to look at. We have a physical system involving the energy of the system. You can very, very nicely characterize the Liapunov function, or approximately what the Liapunov function should take. So recall that this is the system xi dot is equal to omega and negative r omega minus g over L sine theta. And we call that the equilibrium points are when omega is 0 and theta is n pi, where n equals 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on and so forth. And we want to figure out how to choose a Liapunov function. In physical systems, we're going to try and use the energy, the total energy, to determine the Liapunov function. For non-physical systems, so like purely mathematical systems, mathematical examples, or maybe for systems that don't have a clear, that are their application systems, they don't have a clear energy function. We have to be a little bit more careful, and it's a little bit more unclear on how to do that. For physical systems, we can often look at the variation of the energy of the system. Which is really nice. So specifically for this system, if we try the function v of xi, so v of theta omega equal to 1/2 omega squared plus g over L times 1 minus cosine theta, we see that something really cool happens. The gradient of v in this case, with a vector dv d theta dv d omega, which is going to be g over L sine theta and just omega. So the gradient of v dotted with xi prime, which is g of xi, is going to be equal to this times this plus omega times this times this. In which we get a cancellation when we distribute this omega through and subtract. We get this cancels with this, and so we're left with gradient of our Liapunov function dotted with g of xi is equal to negative r times omega squared, which is actually strictly less than 0. R is a positive constant, and omega, as long as omega is non-zero, this is strictly less than 0. But this will always be less than or equal to 0. Now, it's important to point out that this is only a Liapunov function for the even values of n, specifically when n is 0, plus or minus 2, plus or minus 4, so on and so forth. V of xi star n is going to be the 0 squared over 2 plus g over L times 1 minus cosine of n pi, which is equal to 0 for even values of n. And for odd values of n, we don't get as lucky. But this has a physical reason as well. This is equal to 0 squared over 2 plus g over L times 1 minus cosine of n theta, right, n pi, which is 2g over L. So it violates the first condition here for the odd integers n. But this guarantees for us that these equilibrium points for the even values of n are in fact going to be at least stable. But we have a little bit of an issue here because w could equal 0, in which case this is if w equals 0, this value right here is equal to 0. So this only guarantees for us stability. Because of the fact that this, when omega is 0, is equal to 0. This is not a strict Liapunov function. And this is sometimes an issue that we'll hopefully resolve by the end of the lecture today, because we do know that these points for this example function, this example system of differential equations, because of the damping term here, are asymptotically stable. If we open up and take a look at, from the previous lecture, the simulation, where showed from the simulation and we proved using linearization that these even values of n are giving us asymptotically stable critical points. It's right here. Right here, right here, and right here. The problem here is that this function is 0. The Liapunov function that we've chosen is 0 at these points when w itself is equal to 0, or omega itself is equal to 0. And we want to get the result that of asymptotic stability here. So we'll see how to deal with this a little later on in the lecture. And the next example that I want to cover is an example that could definitely be applied in a lot of different ways, but right now I'll just write it down as a direct system. Let's say psi prime is equal to x prime, y prime, which is negative x minus x y squared, negative y plus 3xy squared, x squared y, sorry. Where if you go through and you solve for the critical points or the equilibrium points of this function, I'll note that xi star is the point 0, 0 is the only equilibrium point. And a good question to ask is, how do we find a Liapunov function for a system like this? And I want to emphasize here that it's not trivial and it's not always the same. It depends heavily on the g function. So different g's are going to give you very different Liapunov functions. However, for this one, we note that we have both quadratic functions of our variables, x squared and y squared. And we have a quadratic term in each one of these and a linear term in each one of these. And we note that if you choose function b of xy of the form ax squared plus by squared the gradient of these is 2ax and 2by. And the idea then is to take a function of this form, take the gradient, and we take the dot product with g, hopefully get some simplification that'll simplify to either a strictly negative function or just less than or equal to 0 with a proper choice of a and b. And sure enough, this is what happens exactly. So, taking the gradient of the function v dot product with g, this becomes 2ax times negative x minus xy squared plus 2by times negative y plus 3x squared y. Which simplifies to negative 2ax squared negative 2ax squared y squared minus 2b y squared plus 3 times 2, so 6b x squared y squared. And a choice then of a equal to 3 and b equal to 1 will cancel the higher order quadratic term. So this term right here gets canceled with this term right here. And what's left over is that the dot product of the gradient g simplifies to negative 2 times 3x squared plus 2y squared. Which for any value of x and y, this is always going to be positive, and therefore this is going to be strictly less than 0 for all x, y not equal to the critical point xi star. So by the stability theorem, the critical point 0, 0 is asymptotically stable. And sure enough, if we do a phase plane plot of solutions to this ODE, this is exactly what we see. The solutions very, very quickly, regardless of the initial condition, converge to this point right here. This is a very, very neat example. And the next example is going to be an entire class of functions. This is sometimes called the class of potential functions. So, where the xi prime is g of xi, if the vector field g of xi is what's called conservative, which basically means that g of xi is equal to negative the gradient of some potential function, some scalar potential function, some function psi of xi with continuous partial derivatives equilibrium points of star are the same as the critical points of the function psi of xi1 to xin. Because you'll remember from your multivariable calculus class that the critical points of a multivariable function are where the gradient vector of that function is equal to 0, or d phi xi1 is equal to 0 all the way up to d phi xin is equal to 0. So all of the partial derivatives that are simultaneously equal to 0. And so what we can say then is that if xi star is a critical point, and if the function psi has a local minimum, at psi star, then the function b of psi is equal to psi minus psi at the critical point. This function is a Liapunov function. For star. And this is relatively straightforward to go through and show. The gradient of v at the point psi dotted with g is going to be the same thing as the gradient of psi dot product with negative the gradient of psi, which is negative magnitude of gradient of psi squared, which this will always be positive, and negative times positive is always negative. This will always be less than 0. So for a really good example of this, we'll look at psi is equal to 2D example, x times y times e to the negative x squared minus y squared, where if we take partial derivatives and look at the differential equation, dx dt is equal to d psi dx, which is negative y times 1 minus 2x squared times e to the negative x squared minus y squared, and dy dt is equal to d psi dy, which ends up being negative d psi dy, negative d psi dx, ends up being negative x times 1 minus 2y squared times e to the negative x squared minus y squared. We can go through and figure out the critical points of this function right here, or the equilibrium points of this system of differential equations right here. And this is a function that I use pretty heavily in the multivariable calc class. But there end up being 5 equilibrium points where if you make the notation L is equal to 1 over the square root of 2, these 5 equilibrium points end up being 0, 0, negative L, positive L, negative L, positive L, and positive L, negative L. Not only that, but using the second derivative test from multivariable calculus, gives you a classification for each one of these points. 0, 0 ends up classifying as a saddle point of the function psi. Negative L, and LL is a local max of this function. And negative LL and L negative L are both local mins of this function. So by this example right here in our Liapunov stability theorem, the function psi of xy minus psi at the critical point is a Liapunov function. It's actually a strict Liapunov function for these 2 points right here. And so these 2 points, the 2 local mins, are going to be asymptotically stable. And I'm not going to go through and calculate these zeros. It's a good exercise to go through and do. But this is just a 3D plot showing and verifying for you that L, L right here is the local max. Negative L is the local max. And negative L, positive L is a local min right here. And L, negative L is also local min. So in solving the differential equation, we expect both these 2 points to be asymptotically stable. And sure enough, if we run our Python code and go through and check this, this is exactly what we see. And we'll do that right now and bring the plot over onto the note sheet. Not only that, but the trajectory of the solutions seems very much to follow along with the behavior of this function psi, where we classified this point as a saddle point, these 2 points are local maxes, and these 2 points are local mins of our function psi. These are the asymptotically stable equilibrium points. All of the solutions are directly converging to these points, which is very, very neat. So we'll move on to apply and cover some more definitions that are going to be very useful to us in our next lecture, as well as for the last thing that I want to talk about. The set S in Rn is said to be positively invariant for differential equation star if for each initial condition in S, the solution xi of t, starting with the initial condition xi naught, is also in S for t in some set. 0 to omega. In addition to this, we'll say that the omega limit set, the forward limit set for an orbit with right maximal interval of existence from 0 to infinity is the set of points in Rn such that there is a sequence Tk going to infinity, the positive boundary point of the right maximal interval of existence, such that the solution at these times goes to the point eta. As k goes to infinity. Likewise, we define the alpha limit set in the exact same way, only for the left interval of existence for the orbit. So you can think of it for a given orbit, the limit set is the set of points that are converged to in either the positive time direction or the negative time direction. And these sets are going to be very important a little bit later on when we discuss limit cycles. But what we can go through and prove, this is done in the book, is a slightly stronger theorem than before, or I should say a slightly weaker theorem because it applies to more general cases. If V is a Liapunov function for a star on a bounded open set U, then for any constant C, greater than 0, such that the set of points eta in U such that V of eta is less than or equal to C is closed. This set is positively invariant. So we go back for a second to not this example, but the example prior. This example right here, we ended up showing that this was the Liapunov function with a equal to 3. This is the Liapunov function with b equal to 1 for this system of differential equations. So the positively invariant sets then for this Liapunov function are the ellipses, or the sets satisfying v of xy, which is 3x squared plus y squared is less than or equal to c. And these sets are ellipses that depend on c. But the sets of the form of points x, y, such that 3x squared plus y squared is less than or equal to c, because these are closed sets. These are positively invariant sets for this system. Like I said, the proof of this is in the book. But this definition allows us to greatly go through and actually come up with a better theorem that allows us to address the problem that we had in using Liapunov functions for the pendulum example. This is called the Lasalle invariance theorem. And again, we have let V be a Liapunov function for the differential equation system star on a bounded open set U containing an equilibrium point xi star if c is greater than 0, is a constant such that set S is a set of points eta such that V of eta is less than C if the set is a closed set in Rn, and there is no initial condition in S for which the Liapunov function, the solution is constant on the orbit starting with that initial condition. then for all eta in S, the solution xi of t starting at xi naught, starting at eta I should say, converges to the critical point, the equilibrium point xi star, as t goes to infinity. And the proof of this uses limit sets from before. And positively invariant sets. It's a little bit long, so I'm not going to cover it, but again, it's in the book. But the main way that we can use this theorem and what it's showing is that this theorem shows that under the right conditions, the existence of a Liapunov function implies that solutions in a certain set must converge to an equilibrium point. And this theorem, in this theorem, the Liapunov function does not have to be strict. So this is actually going to resolve the problem that we came up with before when we were investigating the stability of the critical points of the pendulum problem. This last statement right here makes this a weaker theorem, but it makes it better for us and better to use in general. It's more useful because it requires less assumptions on the Liapunov function. So in the pendulum example, if you go back to this example right here, we had a problem where the Liapunov function is constant. It's 0 on this line right here and on this line right here, which makes it not a strict Liapunov function. Yet the point is still asymptotically stable. So this Lasalle invariance theorem rectifies this problem, and we can see that by looking at the following. The orbits of this differential equation, or I should say on any orbit of this differential equation, the solution is never going to be constantly equal to 0. It's only equal to 0 when we cross the W axis here, the omega axis. This is the omega axis. This is the theta axis. So for any orbit, you kind of follow any one of these orbits. The solution is never constantly 0. Therefore we can go through and directly apply the Lasalle invariance theorem to the solutions here. Furthermore, if we take a look at how the Liapunov function is behaving with respect to these critical points, where the Liapunov function that we had was y squared over 2 plus g over L times 1 minus cosine of x. These are the level curves of this function. The gradient is going to be perpendicular to the level curves and pointing away in the direction of increase of the function. So if we look at the regions where v of xy is less than s, these regions correspond to exactly the regions that are surrounding all of the stable critical points. And we can bring, for this example, s all the way up to 2 for the separatrix of these level curves. And even if you change the values of g and L, these regions are going to change, they're going to shift, but the idea is that for various values of g and L, physically speaking on Earth, g would be 9.8. L is the length of the bar, or the rod of the pendulum. We're seeing that these regions are characterizing from the Liapunov function by Lasalle's theorem these stable points of this system of bodies. So this is a very, very neat idea and a very, very neat method that I think has been fully described. And the next lecture that we'll go over is the next topic that we'll cover is getting a better understanding of limit cycles, and when we can determine whether a system of differential equations is going to have limit cycles in the solution, and how to better understand them. But thank you very much for tuning into lecture today. I hope you had a great day.